pages. Okay, so this one that comes up at number 1, ilovemathsgames.com, must have a lot of web pages linking to it. And the way they do that, I mean, I won't go into the details of how that matrix, it's called an incidence matrix on a graph. I won't go into the details how that matrix is constructed. But at the end of the day, what they want is one eigenvector of that matrix. It's actually an eigenvector, or it's actually a vector such that the sum of all the entries equals 1. So it's a vector of probabilities, and it's a vector of probabilities that if you're surfing the web, you will end up at that web page. So the higher the probability, right, the more likely it is you are to end up at that web page. So one thing of interest is if we have, I don't know, so how many web pages are there? What we say, billions? What? 3 billion? 5 billion? I've got no idea, right? But where n is large, the size of the matrix, the n by n matrix, where n is very large, we can ask the question, how do we determine this one eigenvector that we need for these page ranks? And it turns out that's what this lecture on the power method is all about, which is in chapter 35 of the workbook. It turns out what we need for such a calculation is the what's called the dominant eigenvector. And that's what this power method is all about. It's an algorithm. It's an algorithm that produces or estimates the dominant eigenvector of a given matrix. So that's what we're all about today, is, or at least in this first hour, is understanding the power method. So first we'll see how the power method works, and or we'll see exactly what the power method is, rather, and then we'll look a bit closer at it and understanding why it does what it does. I've got some handouts at the back if you can take one. After I finish chapter 35, I'll leave the room for 10 minutes and we'll run the teaching and course evaluations. I've also got another handout just on some a little summary sheet for the final exam. And I'll go over that at the end of the day. All right, so really this is a computational method for estimating what's called the dominant eigenvector and, in fact, the corresponding eigenvalue. So what we've seen so far are just these exact methods of first calculating the eigenvalue of a square matrix by just solving the characteristic equation, and then for each eigenvalue working out the eigenvector. But if we've got a very large matrix, I mean even a 5 by 5, 6 by 6 matrix, it can be incredibly difficult to determine the eigenvalues. All right, not so bad to work out what the eigenvectors are, I suppose, if you know what the eigenvalues are supposed to be. Okay, but now the question is, if we have a very large matrix, here's a 3 billion by 3 billion matrix, let's work out one of the eigenvectors and what's called the dominant eigenvector. So here we'll just define what we mean by that. So let's say we've got a square matrix with eigenvalues, say lambda 1 up to lambda n, such that the absolute value of lambda 1 is strictly greater than the absolute value of all the others. Then in such a case, lambda 1 is what we call the dominant eigenvalue of the matrix. All right, so its absolute value is larger than the absolute values of all the other eigenvalues. This lambda 1, the corresponding eigenvector, we call the dominant eigenvector. All right, so what this algorithm, the power method, does, that I'm going to present, is estimate the dominant eigenvector and its corresponding eigenvalue. All right, so it's just the one eigenvector and eigenvalue pair that it estimates, and that's the dominant one. All right, so I mean, just to establish, exactly what we mean by dominant. Here's this 3x3 matrix that's been travelling with us the last couple of lectures. We know all the eigenvalues and eigenvectors. We know how to diagonalise it. It's a symmetric matrix, so we can also orthogonally diagonalise it. But in this case, we know the eigenvalues are -1, -3, and -4. So just by the definition of dominant, that means -4 is the dominant eigenvalue because it's the one with the largest absolute value. The corresponding eigenvector, I'm pretty sure was this one, or corresponding to eigenvalue -4. Okay, so this is a dominant eigenvector. All right. So is that clear? Everyone understands what is meant by dominant eigenvalue and eigenvector? I mean, very easy to define, right? So here's the algorithm. An incredibly simple algorithm. I guess that's why it's so effective in being applied to, matrices of size 3 billion by 3 billion or however it is. It's a very simple algorithm to implement. All right, so this is the algorithm known as the power method. So what we're going to do is start with a vector. All right, we'll choose a vector, call it u0. Now here, I'll explain this sort of throughout the lecture. You'd think either something is arbitrary or it's not. Here I say u0 is an almost arbitrarily chosen vector. I'll explain that later on, but just for the moment, let's say it's an arbitrarily chosen vector, so it can be anything. But actually, I'll just make a little comment that there are conditions on this initial vector. So what we do is choose an initial vector and then just generate a sequence of vectors. And the way we generate that sequence, so here's the sequence. So we start with u0, which is the one we choose, generate this sequence u1, u2, u3, and so on. And we stop, well, whenever we want to. All right, so u0 is chosen. All right, we choose u0, and this is how we generate the sequence, right? Very, very simple. We take our matrix and multiply the kth vector in the sequence to generate the k+1 vector, or to generate the next vector, right? Very easy to implement. So we start with u0, and u1 is then just a times u0. u2 is just a times u1, and so on. We generate the sequence that way. All right, then for large values of k, what this algorithm does is converge to the dominant, or to a dominant eigenvector. When I say the dominant or a dominant, I mean really it will be only one eigenvector, or I should say any scalar multiple of a vector. Because remember, any scalar multiple of an eigenvector is still an eigenvector corresponding to the same eigenvalue. Okay, so I mean, when I write down a statement like this, saying that this vector 1, -1, 1 is a dominant eigenvector, I mean, I really mean any scalar multiple, any non-zero scalar multiple of that vector. All right, so that's all it's doing. This sequence converges to the dominant eigenvector up to scalar multiplication. And the dominant eigenvalue is determined as follows. So what we do is take, say, the last vector we generate in the sequence, say uk+1, take the jth entry, all right? So this notation here, that means the jth entry. All right, so we choose the jth entry of the last vector in the sequence, then choose the corresponding entry in the vector before, so in the kth vector in the sequence. And this is chosen, this jth entry, well, what is that entry? Well, here we say, I've said usually we choose j. Just scrub out that word usually, and we'll say we do indeed choose j so that the magnitude, so in other words, we choose the entry with largest magnitude. I'll explain more about this in a minute. For the moment, I'm just stating what the algorithm is. Okay, so we generate our sequence. It's a very straightforward thing to do, just by repeated multiplication of the matrix on each vector in the sequence, right? And that generates the next vector and so on. So when we finish, we look in our vector, choose the entry with largest magnitude, choose the corresponding entry in the previous vector, and then just take their ratio. Okay, and that's going to approximate the dominant eigenvalue, and the last or second to last, whichever one, will approximate the dominant eigenvector. All right, so look, this is this next example is with a 2 by 2 matrix. I mean, we can find the exact value of the dominant eigenvalue and work out the corresponding eigenvector. So, I mean, it's really just to demonstrate how we can how this algorithm works, which is not a very complicated algorithm, okay? But it's just good to see how this works. And, I mean, we can even see how it converges after a few iterations. All right, so, look, we can work out the the characteristic polynomial of A is just 3 minus lambda all squared minus 1. Okay, so we work out the eigenvalues. So that's the polynomial, right? The characteristic equation is where we set the polynomial equal to 0 and solve for lambda. All right, so that just so that's just the determinant. Remember, that's the determinant of A minus lambda I, where we subtract lambda off the diagonal entries of A. All right, so this is just 9 minus 6 lambda plus lambda squared minus 1 equals 0 is the characteristic equation. So this is lambda squared minus 6 lambda plus 8, which then factorizes into lambda minus 4 and lambda minus 2. All right, so we've got 2 distinct eigenvalues in this case, and we can see immediately that the eigenvalue 4 is dominant. All right, so that's the dominant eigenvalue. The corresponding eigenvector we can work out exactly as well. So if I subtract 4 off the diagonal, so A minus 4I, V equals 0, we'll have that equation as a matrix, written out as a matrix equation, is just negative 1, 1 in the first row, 1, negative 1 in the second, multiplied by a vector AB equals the 0 vector. All right, so in this case, both row 1 and row 2 imply that A must equal B. And in that case, our dominant eigenvector will just be any scalar multiple of the vector 1, 1. All right, so that's the situation for that particular 2 by 2 matrix. But let's just have a look at what the power method tells us. All right, so what we do in this case is, so we choose an initial vector u0 arbitrarily. So in this case, again, there are some conditions on this initial vector, and sometimes it won't depending on your choice of the initial vector, the algorithm won't do what it's supposed to do. I'll talk about that later. But just to see how it works, to see it in action, I guess, let's choose an initial vector just to be 1, 0. Doesn't have to be this, but we'll work with that. Okay, so now let's generate the sequence. Okay, so if I multiply that initial vector by the matrix A, that will give me the next vector in the sequence. So just multiplying the matrix A by this vector 1, 0, that's just going to get the first column of A. So that'll just be 3, 1. All right, so again, the next vector in the sequence is just A multiplied by the previous one. So U2 is just going to be A times U1, which works out to be 10 and 6. All right, so I can actually write this as approximately 6. So 6 multiplying 1 in the second entry, and it'll be about 1.667 or so in the first. All right, so you get the idea, right? You see how this sequence of vectors is being generated. Okay, it's a very, very simple algorithm to implement. All right, so in this case, we multiply the matrix A right at the top of the screen there by the vector, or rather, we multiply the vector 10, 6 by the matrix A from the left, and we end up with 36 and 28, which I can also write as approximately 28 times 1, and I think it works out to be about 1.286 in here. So that's just an approximation. All right, so does everyone see how the sequence is being generated? Actually, what we end up with is, so I mean, I prepared this one earlier, right? So the seventh, after 7 iterations of, or 7 steps in this algorithm, it works out to be about 8,256 and 8128, all right, which is approximately 8128. So 1 in the second entry, and that's about 1.016. All right, so actually what this sequence is doing, depending on how you look at it, remember, any scalar multiple of an eigenvector is still an eigenvector corresponding to that same eigenvalue. So what this power method is saying is that this vector, 8,256 in the first entry, 8,128 in the second, is approximately the dominant eigenvector of the matrix. All right, but it's just a scalar multiple, and in this case, it's a scalar multiple. It works out to be about 1.016 and 1, which is pretty close to the exact eigenvector that we've worked out. So, I mean, that's part of the algorithm. Okay, so that just gives us an approximation. That's how it works, giving us an approximation to the dominant eigenvector. Okay, so what about, well, let me just make that comment. So the dominant eigenvector is approximately U7, the vector U7. All right, so I mean, you could keep going as long as you want in generating that sequence up to whatever precision you require. All right, so the dominant eigenvalue is approximately U7, which we've worked out to be, I won't write it out again, okay? That's what the power method is telling us. All right, so now let's just apply this one more time. Generate a vector, the next vector in the sequence, U8, which works out to be 32896 and 32640. And what we want to do now is, according to the algorithm, is, well, to estimate the dominant eigenvalue, is take the largest entry in the vector U8. By largest entry, I mean the entry with largest absolute value. Okay, so take the largest entry in that vector and the corresponding component or the corresponding entry in U7, and then take their ratio. All right, so the dominant eigenvalue will be approximately, so the largest entry in this case is in the first entry, so 32896 divided by the entry in the first row of the previous vector, which is 8256. All right, so, I mean, we know the answer is exactly 4. We know 4 is the dominant eigenvalue from our previous calculation. So, well, about 32 on 8, it's looking good. But just works out as an approximation to be about 3.984. All right, so why does that work? Well, there's just one thing to observe why that works. So when we're taking the matrix A multiplied by U7, which equals U8, but what we're saying is if U7 is approximately the dominant eigenvector, it's saying U8 must therefore be approximately the corresponding eigenvalue multiplying U7, that vector U7. All right, so what we can do, in fact, in this case, we could have taken the first or second entry in U8. I'll explain in a minute why we choose the largest, but just for the moment, in this case, we took the first entry and then the corresponding entry of U7. So you can see just from this equation alone, if we take the first entry in U8 and the first entry in U7 and take their ratio, it's going to give us the eigenvalue approximately. Okay, so that's why that works. However, why do we choose the largest one? Well, it so happens that when we implement this algorithm, sometimes, and I mean here it's a very artificial example because it's just a 2 by 2 matrix, right? But if I gave you a very large matrix, chances are one of those entries might be 0, right? And in fact, it could happen that the first entry of the dominant eigenvector might actually be equal to 0. Now, we wouldn't see that in the implementation of the algorithm. But what we'd see is the entries of, see here how the entries in the vectors in the sequence are just getting larger and larger. In some cases, they may not be getting larger and larger, or in some cases, they might. But in some cases, you might find that some entries blow up a lot quicker than others. And in fact, what it's converging to, the entries that are not blowing up quickly might actually be approaching 0. All right? And you don't actually detect that in the algorithm because it may just happen that when we calculate these vectors in the sequence, at some stage, I mean, the entries could be small, but not 0, right? And so if we happen to choose a relatively small entry in the vector, then we may be choosing one that's converging to 0 in the algorithm, all right? Which could give us any result, actually. And therefore, if we specify in the algorithm to always choose the entry in the vector that's largest, that's not going to be converging to 0 because we know actually that an eigenvector can never be a 0 vector. There must always be at least one non-zero entry. Okay, so that explains why we need to choose the the entry with largest magnitude, just to ensure that we're not choosing an entry that is converging to 0 that we may not be able to detect in the algorithm. All right, that just ensures that. All right, but what about this peculiar phrase I used on page 222? So when I said almost arbitrarily, I mean it either is or it isn't, right? What do I mean by that? Well, there are some conditions on that initial vector. Here's an example. Here's something to consider. So for this matrix, we've worked out the dominant eigenvector and the corresponding eigenvalue. But what if I'd chosen let's say, what if we chose u0, that initial vector, to be 1 and -1, right? Is that that's just as good as any other vector, right? Well, let's start generating the sequence corresponding to this vector. Well, u1, which is just a times u0, so the matrix A is 3, 1 in the first row. So that'll give us 2 in the first entry. And in the second entry, it's 1 and 3, so that'll be -2. Oh, so actually this is just 2 times the original vector. So in fact, if I had chosen the vector 1 and -1, that's actually an eigenvector corresponding to another eigenvalue. All right, so there's just a demonstration straight off that if I happen to choose an eigenvector that's not the dominant one, the algorithm's not going to do what it's supposed to do, right? The algorithm's not going to converge to the dominant one. It can't possibly, right? Because the definition of eigenvector, it's only ever going to return a scalar multiple of that other eigenvector. So that just demonstrates that if we choose one of the other eigenvectors as our initial vector, that won't work. And it turns out the problem lies in choosing any linear combination of all of the other eigenvectors except the dominant one, right? If there's no component of the dominant eigenvector in this initial vector, the algorithm won't work. It won't converge to the dominant eigenvector. So right there, we can see some conditions or even assumptions that we need to specify for the algorithm to work. All right. So in other words, what we've shown here, let me just write it down. This vector is an eigenvector corresponding to eigenvalue 2, and I'll say which is not dominant. Okay, so there's a problem there. So I'll just, right, in that, if we were to use that initial vector, the algorithm wouldn't do what it's supposed to do. All right, so we've got some assumptions. So let's just make all of those clear. And actually what we'll do is look through a careful derivation of why the power method works and understand where all these assumptions come from. All right, so there are 3 key assumptions, actually. The first one is that there is a dominant eigenvalue and dominant eigenvector. All right, so that's the first most important assumption. The power method returns the dominant eigenvector and the corresponding eigenvalue. If there isn't one, it's not going to happen. So that's the first and obvious assumption to make. I mean, for example, we might have a matrix, or any size matrix, say, with eigenvalues lambda, say, 1 and -1, and such that so we can see clearly the absolute value of lambda 1 and lambda 2 are the same, but such that these are strictly greater than all of the other eigenvalues, depending on how large the matrix is. All right, so if that's the case, this is saying that, well, we don't have a unique dominant eigenvalue. All right, we've got two. So we're going to get problems there. It's not going to return a unique dominant eigenvector. I mean, it might return a linear combination of eigenvectors corresponding to 1 and negative 1, but it's a little bit, or it may not, the algorithm may not even converge at all. It may just flip back and forth between the two in the end. So anyway, in that case, that wouldn't work. So we assume that there is a dominant eigenvalue and corresponding eigenvector. All right, there's another rather strong assumption that we'll make as well for the algorithm to work, and that is that the eigenvectors of the matrix, V1 up to Vn, are all linearly independent and form a basis of Rn. This is for an n by n matrix. Okay, so in other words, this is saying that if it's an n by n matrix, we're assuming we've got n linearly independent eigenvectors. That's a rather strong assumption as well, right? We've seen an example earlier this week of a 3 by 3 matrix, actually, that doesn't have 3 linearly independent eigenvectors. In fact, I think I gave you an example, but I didn't work through it. I gave you an example of a 2 by 2 matrix that only has 1 eigenvector. Right? That was this matrix. Right? You'll find that only has 1 eigenvector, not 2. In fact, with any non-zero entry here, you'll find that matrix. The matrix would have only 1 eigenvector. All right. So I mean, even there'd be a problem. All right. So that is a rather strong assumption. All right, we're assuming that the eigenvectors form a basis for Rn. So in other words, any vector in Rn can be written as a linear combination of those eigenvectors. And here's the third assumption, and the most peculiar one, I guess, but this comes back to the comment I made earlier about assuming that that initial vector is not just a linear combination of all of the other eigenvectors except the dominant one. So in other words, it's stated like this. We assume that the chosen vector, that initial vector u0, that starts the iteration, well, is non-zero. Okay, we have to say that. Otherwise, we're going to get an incredibly boring sequence of vectors. So we'll assume it's non-zero. But when written as a linear combination of the basis of eigenvectors, okay, from assumption number 2, remember, any vector can be written as a linear combination of the basis, and we're assuming that the eigenvectors form a basis. So we're assuming that that the chosen vector u0 has a non-zero component of the dominant eigenvector. So in other words, it's not just one of the other eigenvectors, or it's not just a linear combination of all of the other eigenvectors except the dominant one. All right, so that's that third assumption is related to the comment I made at the bottom of the previous page. All right, now I will just make a comment about this third assumption, is that this is actually very difficult to enforce. All right, in fact, if we run the power method on a 10 by 10 matrix, or even a 1 billion by 1 billion matrix, what would you choose as your starting vector? All right. If you could pick a vector, or if you could pick an eigenvector of that matrix, that 1 billion by 1 billion matrix, that would be like winning the lotto multiple times over, right? You would be incredibly lucky to do so. However, if it's a 2 by 2 matrix, maybe your chances are pretty good, right? If I give you a matrix whose entries are integers, and you choose an initial vector of 1, 1, right? If I give you a 2 by 2 matrix, well, maybe it is, maybe it's not. If I give you a 100 by 100 matrix who's with floating point entries, okay, that are not necessarily integers, okay, maybe you'd be incredibly lucky to be able to choose such an initial vector that does not contain a component of the dominant eigenvector. So, okay, it's difficult to enforce, but I will just say that failure of this third assumption is actually quite rare, let's say, in applications. Right? It's actually more common, more likely to be a problem in what we might call artificial classroom cases or examples. All right, so just a comment about that. It's difficult to enforce, but nevertheless, there it is. All right, so let's have a close look at all these assumptions put together and what the power method is actually doing. Because it's a remarkably simple algorithm, right? Take your matrix, choose a vector, and just keep multiplying by that matrix, and it converges to the dominant eigenvector. All right, why does that work? All right, so we'll suppose, in this case, that lambda 1 is the dominant eigenvalue of an n by n matrix. Okay, so in other words, its absolute value is strictly greater than the absolute value of all the other eigenvalues. So we're assuming that the dominant eigenvalue exists. All right, so this is just assumption number 1. This is just another way of stating assumption number 1. In other words, assume there is a dominant eigenvalue. Right, so it's non-zero. All right, also, so I've said here for simplicity, we suppose that the matrix has n linearly independent eigenvectors, so it's an n by n matrix. So this is assumption number 2. All right, so we're assuming that any vector with n entries, can be expressed as a linear combination of the eigenvectors, where in other words, we're assuming the eigenvectors form a basis. Okay, so in that case, whatever vector I choose, I'll write it as a linear combination of those eigenvectors, right? Because the eigenvectors form a basis, it means I can do so uniquely. All right, that's what it means to have a basis. All right, so we write out U0 as that unique linear combination of all the eigenvectors. And now we also suppose that, so in this case, we're assuming that V1 is the dominant eigenvector. All right, so we suppose that T1 is not equal to 0. So T1 is the coefficient of V1 in this expansion. So that's precisely assumption number 3. Right? That's just that's a simple way of expressing assumption number 3. That when we write out that initial vector as a linear combination of the eigenvectors, that coefficient, or in other words, the component of V1 is not equal to 0. All right, so we suppose that T1 equals 0. So now let's just start generating these vectors and see what they look like. So we take the first vector U1, which is just A times U0. But since we've got the initial vector expressed as a linear combination of eigenvectors, this is just equivalent to the matrix A hitting each of those eigenvectors one at a time. Right, in the linear combination. But since they're eigenvectors, it means A on V1 is just lambda 1 V1, and so on. So we just get eigenvalues here. All right, and then repeat the process. So multiply this new vector by A, and the same thing happens. Right? We end up hitting each of these eigenvectors, V1, V2, up to Vn, by the matrix A, which introduces another factor of the corresponding eigenvalues. And so what happens after so many iterations, we end up with the kth vector in the sequence just being this linear combination of the n eigenvectors, where each of the eigenvalues occurs in the coefficients, in each coefficient, as a kth power. All right, so the coefficient of V1 here, lambda 1 to the k, and so on. Coefficient of V2, we've got a factor of lambda 2 to the k. All right, now remember, lambda 1 is dominant. So right at the top of the screen here, we've said that the absolute value of lambda 1 is strictly greater than the absolute value of all the others. So if I then take this factor of lambda 1 to the power of k outside of a common bracket, we actually end up with this expression. Okay, now this ratio, lambda 2 over lambda 1, if lambda 1's absolute value is greater than all the others, it means this factor is going to be, well, is going to have magnitude less than 1, right? And in fact, as k gets bigger and bigger, those ratios will get smaller and smaller, all right? And that's the key. That's why the power method works, okay? Because those ratios are getting smaller and smaller, and in fact, in the limit as k goes to infinity, they will vanish. All right? So, in other words, for large k, after a large number of steps, what we have is the approximation that uk is just only this first term involving v1, right? And all the other terms, the coefficients get smaller and smaller. So, that's just the scalar multiple of the dominant eigenvector, right? That's why it works. So we end up with uk for very large k just being approximately lambda 1 to the kth power multiplied by that initial coefficient t1 times the dominant eigenvector. Okay, so in other words, it's just a scalar multiple of v1. All right, and we can also see, I mean, I've already really, I guess, explained why this works. We've already seen then that if we generate one more vector in the sequence, so the k plus 1th vector, so we'll just get another factor, lambda 1 to the k plus 1 times t1 v1. And then if we choose the largest entry in that vector, so in other words, choose it so that it's not converging to 0, all right, we end up with this ratio, which will give us precisely an approximation to the dominant eigenvalue. All right, so the comment here is that it's not going to work if t1 is equal to 0. All right, and in fact, if t1 was 0, the algorithm might converge to the second most dominant eigenvector if it's unique, right? If it exists, if it's unique. And what's more, the convergence, right? The rate of convergence depends on the absolute value of lambda 2. I won't write that down, but it's just a comment. It's just a comment to make. If lambda 2 is the next most dominant eigenvalue, it means these other guys will approach 0 faster than that one. And so the actual convergence of the algorithm depends on the magnitude or the absolute value of the next most dominant eigenvalue. All right, look, I might actually finish up there. This section on deflation, 35.3 won't be examinable, and I'm not going to talk about it. I mean, it's just another numerical algorithm that goes hand in hand with the power method, but I won't talk about it. Instead, what I'll do now is just take a 10 or 15 minute break and let you guys do the teaching evaluations. Now, there's a handout down here. There are some sheets at the back. I'm going to leave the room. I'm supposed to leave the room for 10 minutes, and if you'll indulge me, I'm supposed to read this out to you. So, guys, we'll just get started on this last chapter on complex matrices. This chapter is really worth. It's something just to open your eyes to a world of possibilities that are out there. Anyone who's studying physics, in particular, who's going to be studying any quantum mechanics, this is a lecture for you specifically. But for everyone else, I mean, it really is just contains some results that generalize everything we've seen to date relating to diagonalization of matrices, orthogonal diagonalization, and and related results. So even though I've called this, this chapter Complex Matrices, we could really call it unitary diagonalization, because that's really what this lecture is all about. So remember we talked about orthogonal diagonalization, and we worked out yesterday, wasn't it, in the first lecture yesterday, we worked out that there's this way of characterizing all the matrices which are orthogonally diagonalizable, and these are the symmetric matrices, right? Very simple. It turns out that the symmetric matrices are those which are orthogonally diagonalizable. All right, now these are real symmetric matrices, right, whose entries are real numbers. Now what if you generalize this to matrices which have complex entries? All right, now we can certainly have real valued matrices whose eigenvalues are complex. But what if you just generalize it completely and say, well, now we allow all the entries, or any entry of a matrix could be complex. So what happens in that case? And actually what it does is open up this whole world of many different types of subclasses of matrices. And there are analogues of the orthogonal matrices and the symmetric matrices that we saw yesterday. And it turns out these complex analogues, or the complex counterparts, I guess you could call them, the so-called unitary matrices and Hermitian or self-adjoint matrices. So remember how we defined orthogonal, right? We had this transpose operation that swaps the rows and columns. Okay, so row 1 becomes column 1, row 2 becomes column 2, and so on. So the orthogonal matrices are the ones whose inverse is just obtained by taking the transpose. All right, very easy to invert such matrices. Indeed, this is how they're defined. The symmetric matrices are the ones that are equal to their own transpose. Right, these are the definitions of orthogonal and symmetric real matrices that we saw yesterday. All right, so what we're going to look at now are just the complex versions of these, where the matrices have complex entries. All right, we call such a matrix a complex matrix. Okay, so rather than transpose, we talk about the conjugate transpose of a matrix, denoted A star, or sometimes in the literature, I mean, especially if you're a physicist, you'll see the conjugate transpose written like this, usually said as a dagger, right? This is a drawing of a dagger, right? So a dagger, which is actually given by the transpose of the matrix of complex conjugates. Okay, so this A bar that I've written here is the matrix whose entries are the complex conjugates of the given matrix. All right, so just one thing, if the matrix only has real entries, right, so this is a subset of the complex matrices, then this star operation, the conjugate transpose, coincides with just the ordinary transpose. So remember what these complex conjugates are. If we have a complex number, z, which is written as a plus ib, where I is the imaginary unit that squares to -1. The complex conjugate of this complex number is obtained just by changing the sign of the imaginary part of that complex number. All right, and is usually denoted with a bar over the symbol. So if z is equal to a plus ib, then the complex conjugate z bar is given by a minus ib. All right, so for example, this 2x2 matrix with complex entries called A, so we can first work out the matrix with corresponding complex conjugates. So that'll just be 3 minus 7i negative 2i in the first column, and 0 and 4 plus I in the second, as the entries in the second column. And then we take the transpose so that A star is just the matrix of complex conjugates, all transpose. So the first column becomes the first row. So 3 minus 7i and negative 2i in the first row, and 0 and 4 plus I in the second. All right, so that's what's involved in determining the conjugate transpose of a matrix. All right, so let's have a look at the definition of these so-called unitary matrices. So a complex matrix, now that we've defined the conjugate transpose, a complex matrix A is said to be unitary if its inverse is equal to the conjugate transpose. So just compare this with the definition that we've seen of real orthogonal matrices. Those are the ones whose inverses are just the ordinary transpose. So now what we're doing is generalizing this a bit from orthogonal to unitary by taking the conjugate transpose. All right. Also remember this, that a real matrix is orthogonal if and if and only if its columns form a mutually orthogonal set of unit vectors. Oh, okay, here it says orthonormal. Now for complex matrices, this property is what characterizes the unitary matrices, except rather than using the ordinary dot product that we're used to, we need to use what's called the complex inner product or the complex dot product. So we actually need to change our definition of inner product or our definition of the dot product. All right, well, let's have a look at why we need to do that first. If we're considering vectors whose entries are now complex numbers, all right, what we'll see is actually the ordinary definition of dot product is unsatisfactory in some sense. All right, so let's just remember what the ordinary dot product is. I mean, we've seen it so many times, right? But if we've got two vectors, u and v, in Rn, so they're n-dimensional vectors, okay, so, or vectors with n entries, u and v, remember the dot product is just determined by multiplying the corresponding entries and taking their sum. All right, so u dot v is just u1 v1 plus u2 v2 and so on. And in fact, this could also be written as v transpose times u. Or in fact, I think I mentioned this yesterday, or we could write it as u transpose v. It doesn't really matter. All right, both of these will give us this linear combination of the entries. All right, and what's more, the magnitude of the vector, or the length, which is actually a real number. Why did I say that? Well, it's going to be important later on, believe me. So the length or the magnitude of the vector is just given by the square root of the dot product of that vector with itself. All right, so what we can do is see how this definition of dot product works in the case where we've got vectors with complex entries. All right, and in fact, what I can do is just choose one example where we can see it's not really suitable. The definition is, well, as I said, unsatisfactory. All right, so consider this non-zero vector with entries, complex entries, where the first entry is the imaginary unit I, and the second entry is 1. Okay, so this is just a vector. I've written it as a row vector, but I mean, you could still think of it as a column vector. So if we want to now use the regular dot product to work out the definition of the magnitude of this vector, that means we would take the sum of the squares of the components and then take the square root, right? And that's going to give us the magnitude. Well, how would that work in this case if the entry, if the first entry is the imaginary unit I and the second entry is 1? You can see immediately that the length of this vector, or the magnitude of this vector, is going to be the square root of I squared plus 1, or 0. And this is where the definition breaks down, is that if we use the ordinary dot product defined for real numbers in the complex vector space, then that means we would have non-zero vectors whose lengths or magnitudes are 0. All right, so there's something not quite satisfactory about that. Right, we only want the vectors with 0 magnitude to be the 0 vector. All right. So that would be a non-zero vector with length 0. So that's just motivating why we would need to change the definitions. All right. So what we're going to do is use what's called the complex inner product, which is defined as follows, or the complex dot product. What we do is, this is probably the most useful definition for it, rather than taking the product as in the regular matrix product, where here V transpose is a row vector, U is a column vector, so V transpose U is just a number. Then instead what we take is the conjugate transpose of the vector V. All right, and we end up defining the complex dot product as just this sum of not the products of entries, but where we first take the complex conjugate of all the entries in V, right, and then multiply up the corresponding components of U and take their sum. All right, so this is just one way of defining the complex dot product as the conjugate transpose of the column vector V, which would be a row vector, multiplying, as in regular matrix multiplication, the column vector U. All right, and so in this case, if we define the magnitude of a vector to be the square root of the dot product of that vector with itself, where this is the complex dot product, or the complex inner product, then the only time we'll get vectors of magnitude 0 is if it's the 0 vector. All right, the reason is when you take if you consider taking the product of a complex number with its conjugate transpose, so if this, with its complex conjugate, so that would be A minus BI times A plus, plus BI or plus IB, which would just be the difference of the two squares, A squared plus B squared. All right. So in that way, we always end up with a real number inside this square root. Okay, remember I squares to -1. Okay, so I should say in general, this is a complex number, right? The complex dot product gives us a complex number, but in the case where we take the dot product of a vector with itself, it's always going to be a real number, as you can see here from that calculation. All right, so that's using the complex dot product then. That has some meaning if we were to go back up here and read over this statement, is that now the unitary matrices are those matrices whose columns form a mutually orthogonal set of unit vectors, but under the complex dot product now, right? Measured under the complex dot product rather than the ordinary real dot product. Okay, so that's the definition of unitary matrix. What about, I mentioned Hermitian matrices. So the unitary matrices are those which, generalize the real orthogonal matrices. Another thing we've seen is the class of real symmetric matrices. So what's the complex analogue of those? We call them Hermitian, or self-adjoint, right? So a complex matrix A is called Hermitian or self-adjoint if it equals its own conjugate transpose. All right, compare that with the real symmetric matrices. Okay, so remember, real symmetric matrices are those which equal their own transpose. All right, so this is the complex version of that. And one thing I told you yesterday was that the real symmetric matrices were very easy to identify just by observing this symmetry about the main diagonal. I mean, you can see it straight away when you look at a real symmetric matrix. You can see that the entries in row 1 are the same as the entries in column 1. The entries in row 2 are the same as the entries in column 2. Well, it's very easy to identify these Hermitian matrices as well. And so I've actually given 3 examples here of just the generic Hermitian matrices. So here, these numbers, the A's and the B's, are all meant to be real numbers. So I've written out the complex numbers in terms of their real and imaginary parts. All right, so there's one observation we can make, or actually a couple of observations we can make about these Hermitian matrices. First observation is that the entries on the diagonal are only ever real numbers. All right. Secondly, we observe this symmetry about the diagonal entries. So, for example, by symmetry, I mean if I look at the entry in row 1, column 3 of this 4x4 matrix, and then look at the entry that's symmetric about the, or its mirror image about the diagonal. So that's row 1, column 3. If I go to row 3, column 1, and compare these, you can see they actually, they're just the complex conjugate of each other. All right, so the entry in row 1, column 3 is the complex conjugate of the entry in row 3, column 1. And this pattern is true for all of the off-diagonal entries. So that's the property of Hermitian matrices. Like their real symmetric counterparts, they're very, very easy to identify, so very easy to spot. All right, one of the most important results of relating to Hermitian matrices is that their eigenvalues are real. And in fact, we'll just observe that in all of these examples, if I set the b's equal to 0, right, if I set all the b's equal to 0, we find that we've got the real symmetric matrices. Okay, so all the b's equals 0, we get real symmetric matrices. That's telling us that the real symmetric matrices are actually a subset of these Hermitian, the complex Hermitian matrices. So any result that holds for Hermitian matrices also holds for real symmetric matrices. Now, I made a comment yesterday that the real symmetric matrices only ever have real eigenvalues. Well, that result is contained in this result for Hermitian matrices. So we'll just make a note of that all real valued symmetric matrices are Hermitian. All right, and so this is just a proof that Hermitian matrices have real eigenvalues. We'll just run through it fairly quickly. I mean, it's a straightforward proof, but quite clever, I think. So remember the definition of eigenvalue and eigenvector. So here I've just written out that equation, AV equals lambda V. All right, so what we'll do, so now we'll assume that A is a Hermitian matrix. Okay, so we'll assume that A is equal to its own conjugate transpose. All right, so this is just the definition of eigenvector and eigenvalue. All right, so we let V be an eigenvector with corresponding eigenvalue lambda. So now what we'll do is take this equation and just multiply both sides from the left by the conjugate transpose of V. So we'll multiply by the left from the left on both sides of the equation by the V star. And remember, this is a well, V is an n by 1, can be thought of as an n by 1 matrix. A is an n by n, and V star is a 1 by n. So this is just a number, right? V star AV is just a 1 by 1 matrix, or a number. Okay, and similarly, remember how we've defined the complex dot product, right? This V star V is just the complex dot product of V with itself, okay? Which is a real number, right, as we've seen. Okay, so one thing we can observe about this product of the matrices, the product V star AV, is if we take the conjugate transpose of that, all right, using this property, I mean, that's just a property inherited from the transpose. I think I've stated that result just for the regular transpose. The property carries over to the conjugate transpose as well, that if we take the conjugate transpose of a product, we end up with a product of the conjugate transpose, but in the reverse order. Okay, so if we now apply that to this product here, so what we end up with, so working from the right to left, we'll end up with V star, then A star, and then V star all star, which equals V. All right? So we end up with V star. Remember, A is a Hermitian matrix, so it equals its own conjugate transpose, so A star equals A. And then if I take the conjugate transpose twice, I end up right back where I started. So in other words, what we've just discovered is that this product, V star AV, is equal to its own conjugate transpose, right? But I've just finished pointing out that it's a number. All right, it's a 1-by-1 matrix or a number. So in other words, if it's equal to its own conjugate transpose, it means it's a Hermitian matrix, right? That's the definition of Hermitian. But it's also a 1-by-1 Hermitian matrix. So what was the observation that we made earlier about Hermitian matrices is that the entries on the diagonal are real. Okay, so in other words, we can conclude since this 1-by-1 matrix is Hermitian, it means that single entry in the matrix must be a real number. Okay, so in other words, what we've got is an equation now, up here, equation 15. We've got an equation that says a real number is equal to lambda times a real number. And so the conclusion then, and that's what's stated over the page, the conclusion is just that, well, lambda has to be a real number. There's no way it can possibly have a non-zero imaginary part. All right, so we've got an equation. This equation 15 is of this form, x equals lambda y, where x and y are both real numbers. There's no way that lambda can be complex. All right, or there's no way that lambda can have a non-zero imaginary component. So the conclusion is that lambda must be real, hence all Hermitian matrices have real eigenvalues. And also, we get for free, since all real symmetric matrices are Hermitian, we also have that all real symmetric matrices must have complex eigenvalues. Just an aside, I mean, you might think, well, why is that special? I mean, don't all real matrices have real eigenvalues? So let me give you a matrix. Hang on, let me think about this. What if I square this, take the product of, or if I square that matrix, that 2-by-2 matrix, what's that equal to? So just regular matrix multiplication. That's -1, 0, and 0, -1, which is just equal to -1 times the identity. Okay, so what we've actually got is a matrix representation of the imaginary unit, right, whose entries are real numbers. All right, so this is a 2-by-2 matrix that when I take the square of that matrix, it equals to -1 times the identity. Try working out the eigenvalues of that matrix. Right? I would expect that you would get plus or minus the imaginary unit I. All right, so there's just an example of a 2-by-2 matrix whose eigenvalues are complex. All right, I mean, you can see it straight away, right? If you subtract lambda, so if you take the determinant of this matrix, that's going to be lambda squared plus 1, right? So if you set that equal to 0, you're saying you're looking for lambda values of lambda which square to -1. So yeah, that's an example of a real matrix that has only complex eigenvalues. All right, anyway, just to give you an example, if you don't fully appreciate why this result is significant about the real symmetric matrices, is that we can say for sure is that their eigenvalues can only ever be real because they appear as a subset of the Hermitian matrices. All right, so one thing we saw about this relationship between well, we saw that yesterday there is a relationship between the symmetric matrices and the orthogonal matrices. And the main result is that a matrix is symmetric if and only if it's orthogonally diagonalizable. All right, so now what we've done is gone to the complex world, right, and we've seen the complex counterparts of symmetric and orthogonal, namely the Hermitian and the unitary. So does this result about diagonalizability generalize? Does that lift up to the complex world as well? Well, it turns out it does to some degree, but actually it turns out the class of matrices which are unitarily diagonalizable, okay, that is, which are diagonalizable by a unitary matrix, are not just the set of Hermitian matrices, but a larger class known as normal matrices. So first, I guess, before we go into that discussion, let's define exactly what we mean by unitary diagonalization. And having seen orthogonal diagonalization and having seen the complex dot product, it should come as no surprise to you, right? So we say a square matrix with complex entries is unitarily diagonalizable if there exists a unitary matrix P. Right, so remember that's a matrix whose inverse is equal to the conjugate transpose. So a unitary matrix P, so that P inverse equals P star. All right, so hang on, let me read that sentence again. A square matrix A with complex entries is said to be unitarily diagonalizable if there is a unitary matrix such that this product P star AP is a diagonal matrix. All right, so it's exactly like the definition of orthogonal diagonalization, except now we're using unitary matrices instead of orthogonal ones. And so those are the matrices whose inverse, so that P star is the P inverse, right? So it's exactly the same product. The P inverse AP equals a diagonal matrix, but now P inverse is P star. All right, so I guess this next couple, or this next sentence is just saying, well, it's natural to consider which matrices are unitarily diagonalizable, and you might think, well, we've seen the orthogonal diagonalization. We know that there's the symmetric matrices, right? The ones that are orthogonally diagonalizable, they're all the symmetric matrices, end of story. So how does that generalize to the complex world? Well, it turns out it's not as simple as just saying it's the set of Hermitian matrices. It turns out it's a much larger class of matrices known as the normal matrices. Normal matrices are just defined to be matrices that commute with their own conjugate transpose. Right? So when I say commute, I mean I'm talking about a commutative algebra here. Generally, the algebra of matrices is not commutative, so generally AB does not equal BA, right? The order in which we take the multiplication is important, right? But in this case, if A times A star equals A star A, those two matrices are said to commute, and this is the definition of a normal matrix. So it actually, and they're not easy to inspect. They're not easy to identify by inspection, right, as I've said here. But it turns out all of these matrices I've just defined, and then some, fall into this very large class of matrices known as normal matrices. So the unitary ones, for example, are the ones where A times A star is the identity. Right? The unitary matrices are the ones whose conjugate transpose equals their inverse. So it doesn't matter which order we take that. So they fall into the set of normal matrices. The Hermitian matrices are the ones where the matrix A equals its own conjugate transpose. So that implies that if I take A times A star, this is just equal to the matrix A squared. And so in that case, it doesn't matter what order I take the product. Right? So the Hermitian matrices also fall into that class. What are called real skew-symmetric matrices, satisfying A transpose equals negative A. Any diagonal matrix, which I guess fall into the class of Hermitian matrices, and there could be others. All right? So that's just to demonstrate that the normal matrices are a much larger class of matrices, or a much larger set than just the Hermitian ones. Okay, so not so easy to identify. I mean, just to convince you that that's not really they're not only the unitary and Hermitian and real skew-symmetric matrices. I mean, we can have others. So, I mean, it turns out this matrix, this 2 by 2 matrix, is normal. But what we want to do is try and work out exactly why. So, what if I take the conjugate transpose of this matrix? So, in other words, if I take the complex conjugates of all the entries and then take the transpose. Oh, sorry, I didn't see your hand up there. Sorry.
You said the diagonal matrices fall into the Hermitian class.
Yeah. Yep.
Does that mean diagonal matrices don't have complex parts to it?
Real diagonal actually, that's a good point. Sorry, I should have said real diagonal matrices fall into the class of Hermitian matrices. Thank you for pulling me up on that. But, I mean, it actually turns out that any complex diagonal matrix is normal. Yeah, let me just clarify that. So real diagonal are a subset of the Hermitian. Yeah, well spotted. So, okay, now taking the conjugate transpose of this 2 by 2 matrix. So let's just look at row 1 first and take the conjugate transpose of each entry in row 1 and then place them into column 1. So we'll have 1 and 1 minus I in that first column. And then the second row, 1 plus I and negative I, will have 1 minus I and I in the second column. Okay, so one thing is this matrix is certainly not equal to A, so that implies it's not Hermitian. Okay, we can see straight away it's not Hermitian. All right, what if I took the product of this conjugate transpose with the matrix itself? So 1 minus I, 1 minus I, and I, multiplied by A itself. So how does this work out? So here we end up with 1. So in the first entry we'll end up with 1 plus the difference of the two squares, 1 and I squared. So we'll end up with 3 in that entry. Here we'll take 1 minus I plus I minus 1, so that entry will be 0. In the second column, we'll have 1 times 1 plus I minus I times 1 minus I, so that's also going to be 0. And then here we'll have the difference of the two squareds, 1 and I squared, which is 2, plus 1, so we'll have 3 here. So actually that's not quite equal to the identity, so we can say that that implies this matrix is also not unitary, okay, just as an aside. But what we've found here, though, is that A star times A is equal to 3 times the identity, which implies, if I just divide this equation by 3, it means 1/3 times A star times the matrix A is equal to the identity. So we've actually got the inverse of A. So it's a scalar multiple of the conjugate transpose. So we're close, but it's not unitary. All right, it's not quite unitary. So in this case, from that we can deduce that A times A star is 3I, which is also A star times A. All right, so from that we can conclude that this matrix A is normal. So just by checking how it checking that it commutes with with its own conjugate transpose. All right, look, I mean, the reason I went through that example, I mean, it demonstrates that the algebra of complex numbers is not so intuitive. And especially once we put them into matrices, right? So, I mean, we'll see it especially in this example. So this is one of the main results. Okay, so I mentioned at the start of this hour that I could have easily entitled this chapter Unitary Diagonalization. And so the big result of this chapter is that the normal matrices is equivalent to the set of unitarily diagonalizable ones. Compare that, so confer, with real symmetric equals the orthogonally diagonalizable matrices, which is what we saw yesterday. Okay? So this is the complex version of that. So it turns out it's not just the Hermitian matrices that are orthogonally diagonalizable, it's the much larger class of normal matrices. And I'm not going to prove this at all. The proof is quite complicated. But here's the result in the box here, that an n by n complex matrix is unitarily diagonalizable if and only if it's normal.